So, last time we explained about a new method to calculate nonlinear response. So if we make them to program, it look like this. Firstly, you need to make all the constant calculate every step, because k will be changed every step. So it's not be k1, it should be k. Although k will be changed every step, and you will use this constant to calculate response, acceleration, velocity, and displacement. After calculate this, you will do a nonlinear part of calculation to decide k for the next step, for the future step, and you save all the things. So if you conduct this program, you can get this kind of response of bilinear. It looked like a little bit like bilinear. It's not linear. It's a displacement to force relationship. Is look like a little bit bilinear. We expected. However, you can see the nonlinear force is not exactly the hysteresis loops that we are expecting to. The force should be same yield force, same place to yield force. So what's happened to them? What's wrong with them? Actually, because we changed the stiffness k for the next time before we calculate the response. So every step, the k has a little bit of error due to the dd, because dd is already over the yielding displacement. However, we didn't count it for the force. So the force calculation have a little bit wrong in here, and all response also being influenced by this kind of error. So to consider this kind of error, we need to more advanced method to deal with that. Here we just introduce. There are a lot of methods to do with nonlinear calculation. For example, when we realize that there is nonlinear happened in this step, we just separate this step for another 10 small step, and do this more 10 times until the change of force delta F is very small, or the dd is very small. However, we need to do some method that is more fast and more effective. So today I'm introducing you a method, a Predictor-Corrector Method. Predictor-Corrector Method is very interesting method, because we are expecting this kind of nonlinear force displacement relationship. So last time we introduced that the three status of yielding and unloading and its condition. And we introduced their parameters as dy, df, k1, k2. And here, a new concept is introduced here to consider the bilinear model to two parts. The displacement is the same. However, when we calculating the force, when consider force has two parts. One is a linear part, another is nonlinear part. So what means is that this is a linear part and this is a nonlinear part, and we just plus them together, it all becomes the bilinear model we are expected for. So for any kind of case of bilinear force like this, we can find a middle axial here, right? Is always parallelized with the nonlinear part with the plastic domain. Okay, and this is passing through the orange point, the cross point here, and this line this gradient is parallel to here, so this gradient is equals to K2. So its force can be always calculated whenever it's linear or nonlinear calculated by K2 multiple D. This is a linear part. And if we don't consider, if we delete the linear part from the whole hysteresis curve, we'll get this kind of part. This is a nonlinear part. A nonlinear part is a little bit complicated, so we can calculate it by more detailed rules. So linear force we can calculate by this. So nonlinear force is first stiffness is K1 divided by K2 because of this is K2. So this is K1 divided by K2. So for the nonlinear part, they didn't have a second gradient. They didn't have a second gradient because the second gradient is K2 minus K2 equals 0. So they have a top force, or we say it's critical force. We say it's QC. Okay, so QC is equals to K1 minus K2 dy. This is constant. It's constant. So you cannot go over this QC. Always lower than QC and larger than minus QC. So firstly, what we do is consider the force is equals to elastic force plus plastic force. So this is total force. We consider them as elastic force plus plastic force. For elastic force, we calculate use n plus 1 multiple K2, n plus 1 multiple K2 calculate this force. And for the plastic part, for the case of linear, we calculated them with the last steps plastic force plus the incremental of d n plus 1 multiple K1 minus K2, because we don't know that what happened until last time. We don't know what's happened in this type. So we firstly consider this type is linear and calculate them, use the n step plus the incremental of K1 minus K2 to the dt, get this. However, in case of yielding, it will go over the QC. They go over the QC if we calculate them by this equation. So RP is larger than QC. So in that case, we firstly let them go down. Or if they are smaller than minus QC, we firstly let them equals to QC. So use the equation to express as if RP n plus 1 is larger than QC, let RP equals QC. If RP is smaller than minus QC, so let RP equals minus QC, because they cannot go over the boundary here. So once they go over, we try. If they go over, we let them down. If they didn't go over, then that's fine. If they go over it, we just let them down. Go over it, let them down. So by this kind of history rule, and we plot them together, we can get this kind of total hysteresis curves like this. So let's summarize the hysteresis rules here to calculate the force. Firstly, we calculate the elastic part force, okay, by the K2 multiple d n plus 1. And then we calculate the n plus 1 step is plastic part force. By n steps, last steps force, plastic force plus the incremental of K minus K2 to the d n plus 1. This is incremental plastic force. However, the total plastic force, if the total plastic force larger than QC, then let them equals to QC. If smaller than QC, then let them equals minus QC. And then we calculate, when we convert RP, we calculate R equals RE to RP. So they will always follow into the elastic rules, no go over and no underestimation. So this time, let us try incremental force method. We calculate the equations using the incremental equation, but with the force also as incremental term. And only we need to do is using delta Vn plus 1 to instead delta N plus 1 by the equation of this equation. So inside, step them inside the equation. And then we can get this kind of equation. Delta An plus 1 is the only unknown variable here. So we can easily get this kind of equation and get n plus 1, delta An plus 1 out. And however, in the typical incremental method, we can see that we can use delta n plus 1. However, we can also plus k delta predicted n plus 1. This means the predicted, and minus k plus predicted. So they are the same with the equation before. However, we have the term with dm k delta d n plus 1 like this. So we calculate this part and this part together. We get delta n plus 1 minus k delta n plus 1. So realize that this part is exactly with if we use incremental method to predict the response, displacement, velocity, and acceleration. So this part is exactly the same with prediction. However, this side are different. So we can consider the force here. Delta Fc is a corrector force because this is a predicted force incremental. So this is a real. After we calculate nonlinear force, we get the real incremental of the force. So the real the force minus the predicted force equals to the corrector force. This force part of incremental that we need to correct the equations. And we write the equation like this: incremental method plus force corrector part here, and we can calculate all the things the same until here is incremental method, but only with one term, that is force corrector. So because this part until this part is the same with the predictor method, incremental method, so we can calculate the delta f predictor as here, and this is corrector here. So this part is what we calculate for prediction, and only this part is for correction. So the real force after real acceleration incremental is the predicted acceleration incremental minus the corrections. So we can easily calculating the real delta an plus 1 by the predicted delta an plus 1 minus correction an plus 1 delta an plus 1. Using the correction an plus 1, we can just calculate that like delta fc minus m hard. The m hard we don't need to calculate again because every step will be same. Use the force stiffness. So because calculating the velocity and displacement is using this equation, and this part before we calculate the correct one, we calculate with predicted acceleration. So with corrector acceleration, we can use delta AC n plus 1 equals delta FC divided m hard, where delta FC is a corrector force. This part is real incremental of force, and this part is predicted incremental of force. So the real delta an plus 1 is equals to the predicted delta an plus 1 minus corrector an plus 1. And Vn plus 1 also the same thing, predicted 1 minus half. Remember, this part have a correction with delta AC n plus 1, and this part have a correction of delta AC n plus 1 by beta delta t square. So we can update our response by this equation. So as a summary of this method, firstly, we just predict the velocity, acceleration, displacement by the incremental method, and then we calculate the bilinear force, and then we calculate the corrector for acceleration, and we update all the acceleration, velocity, and displacement response. So as we explained today, this predictor-corrector method, so you can use this method for your assignment 3.